PCA in 30 minutes. My promise is simple. In the time it takes to drink a coffee, you will fundamentally change how you see data. You've been there, right? You get a data set with hundreds of features. Financial indicators, medical measurements, sensor readings. How do you even begin to visualize it? How do you find the real signal hiding in all that noise? Just staring at a spreadsheet is impossible. It's just a wall of numbers. This is the exact problem principal component analysis was built to solve. It takes your high-dimensional mess and transforms it into a new, clean coordinate system. The new axes of this system are called principal components. Now here's the key. These new axes are ordered by how much of the data's story, its total variance, they actually capture. Now we go straight to the core engine. This is our roadmap. By the end of this course, you will understand all of this. You'll get the covariance matrix, or sigma, and know how it mathematically summarizes the total shape of your data. You'll master the eigenequation, that's sigma v equals lambda v, and see why its eigenvectors are the precise directions of maximum variance. We'll then use those to build the principal components themselves. We'll even learn how to use eigenvalues, or lambda, to measure the importance of each component. And finally, we'll interpret everything using scores and loadings to uncover real insights. This isn't just theory. This is the machinery that powers facial recognition, stock market analysis, and even genomic research. You're about to learn exactly how it works. So let's begin. All right, let's build the single most important intuition you need for PCA. At its heart, PCA is a hunt for the most informative viewpoint of your data. Think of it like finding the main street of a city from a satellite photo. What would you do? You'd look for the longest, busiest road, the one where most of the action is happening. PCA does exactly this, but for data. Let's make this real. Consider a simple problem, student performance. We survey a bunch of students and we record just two features, the hours they studied and their final exam score. So for example, in this table, you can see student A studied for 2.5 hours and got a 65, while student F studied for 6 hours and got a 92. So we plot this data, hours studied versus exam score. It forms this kind of stretched out cloud of points. Now here's the big question. How can we best summarize this trend with a single line? Your first thought might be linear regression, but PCA has a totally different goal. Linear regression's goal is to minimize prediction error. It finds the line that best predicts y from x. PCA, on the other hand, its goal is to maximize data variance. It finds the line that captures the most information, the most spread. Here's the killer intuition. Let's use an analogy, casting shadows. Imagine a light source shining down on our data points from far away. PCA's job is to rotate that line until the spread of the shadows is as wide as humanly possible. That line, the one that captures the absolute maximum amount of spread, is your data's first principal component, PC1. It's the main street. It's the single most important direction in your entire dataset. Just look at these two examples of good versus bad projections. The top line, PC1, spreads the shadows out perfectly. The bottom line just bunches them all together. It's useless. Okay, so we found PC1. But there's still variance left over, right? The points don't fall perfectly on that line. There's more information to capture. So the goal now is to find a second line that captures the most of the remaining variance. But there's one non-negotiable rule. This next direction must be orthogonal to PC1. Orthogonal? It's a fancy word, but it's simple. It just means perfectly perpendicular, a 90-degree angle. And just like that, we have a brand new coordinate system, perfectly aligned with our data. You have PC1, the main street, and PC2, the busiest cross street. Then would come PC3, the next busiest, and so on and so on. This visual hunt is great for intuition. It really is. But how do we find these directions mathematically? We can't just eyeball a 100-dimensional data set. We need to formalize the goal of PCA. We need to find the unit vector, which we'll call U, that maximizes the variance of the projected data. So here it is in this formula. We want to maximize the variance of x times U, subject to the constraint that the norm of U equals 1. In other words, U has to be a unit vector. Now, this looks complicated, but the solution is one of the most elegant results in all of linear algebra. The solution is the principal eigenvector of the data's covariance matrix. But what on earth does an eigenvector have to do with maximizing variance? That probably feels like it came out of nowhere. Let's connect the dots. This is the aha moment. There are two keys to unlocking this. First, the eigenvector definition, which you see on the left. Sigma v equals lambda v. A matrix times its eigenvector is just that same eigenvector scaled by a number, lambda. And second, the variance formula on the right. It turns out the variance we want to maximize can be written as U transpose sigma U. So what happens if we plug an eigenvector, let's call it V, into that variance formula? The variance becomes V transpose sigma V. But wait, we know from the definition that sigma V is just lambda V, so let's substitute that in, which gives us V transpose times lambda V. And since lambda is just a number, we can pull it out front, leaving us with lambda times V transpose V. Now for the final step. Since V is a unit vector, V transpose V is just the dot product of a vector with itself, which is 1. So the whole thing simplifies down to lambda. This is it. The variance in an eigenvector's direction is exactly its eigenvalue. It's not a coincidence, it's the entire reason this works. Let me give you the final geometric intuition to lock this in for good. The covariance matrix, sigma, defines the shape of your data cloud. In 2 dimensions, that shape is an ellipse, like you see in this diagram. The eigenvectors are the axes of this data ellipse. They point along the directions of pure stretch. And the eigenvalues are the lengths of those axes. They literally measure the amount of spread in those directions. So to find the direction of maximum variance, you just find the eigenvector with the largest eigenvalue. It's that simple. Eigenvectors aren't just some abstract concept from a math class. They are the fundamental directions that define the geometry of your data's spread. You know the why. Now it's time for the how. I want you to think of this next chapter as a recipe. A reliable 6-step recipe that works every single time. Here's our roadmap for the PCA algorithm. First, we'll center the data. This shifts everything to the origin to focus purely on its spread. Second, we compute the covariance matrix. This is the mathematical blueprint of our data's shape. Third, eigendecomposition. This is where we extract the directions and their importance. Fourth, we sort the eigenpairs, ranking our new axes from most important to least. Fifth, we project the data to calculate the new coordinates for each point. And finally, step 6, we choose components, using those eigenvalues to quantify exactly how much information we've captured. Let's begin. Steps 1 and 2, center the data and build the covariance matrix. Here's our data, simple and clear. 5 samples, 2 features, x1 and x2. So, step 1, center the data. Why do we do this? Well, PCA is all about variance around the mean. So we shift the data to the origin, to 0, 0, to isolate that spread. The action is simple. For each column, we find the mean and subtract it. The mean of x1 is 1 plus 2 plus 3 plus 4 plus 5 divided by 5, which equals 3. The mean of x2 is 2 plus 3 plus 5 plus 6 plus 9 divided by 5, which is 5. And centering is complete. This table shows our new centered data matrix, which we'll just call x. For sample A, x1 becomes 1 minus 3, which is negative 2. And x2 becomes 2 minus 5, which is negative 3. We just do that for every single row. Easy. Now for step 2, compute the covariance matrix, sigma. Why? This matrix is the mathematical blueprint of our data's shape. It summarizes all the variances and correlations. The action? We use the formula you see here. Sigma equals 1 over n minus 1 times x transpose x. Let's break that down. First, we need the transpose of our centered matrix, xt. You can see it here. We've just flipped the rows and columns. Next, we multiply x transpose by x. This is the main event. For example, to get that top left entry, we take the dot product of the first row of x transpose and the first column of x. So that's negative 2 times negative 2 plus negative 1 times negative 1, and so on, which gives us 10. When we do that for all the entries, we get this matrix, 10, 17, 17, 30. And finally, to get our prize, the covariance matrix, we just divide by n minus 1. Since we have 5 samples, we divide by 4. This gives us our final covariance matrix, 2.5, 4.25, 4.25, and 7.5. This is the complete mathematical description of our tilted data cloud. Now for step 3, the magic of eigendecomposition. This is where the real magic happens. So eigendecomposition, why are we doing this? We're going to crack open that covariance matrix to find its eigenvectors, which are the new axes, our principal components. and its eigenvalues, which are the importance score or variance for each of those axes. Our goal is to solve the equation you see right here, sigma v equals lambda v. To do that, we start by finding the eigenvalues, lambda. We solve what's called the characteristic equation, the determinant of sigma minus lambda 1 equals 0. Given our covariance matrix, let's solve for lambda. First, we set up the equation. We just subtract lambda from the diagonal of our matrix. So we have the determinant of the matrix 2.5 minus lambda, 4.25, 4.25, and 7.5 minus lambda equals 0. Next, we expand the determinant. For a 2 by 2 matrix, that's just a D minus BC. This gives us 2.5 minus lambda times 7.5 minus lambda minus 4.25 squared equals 0. When you multiply that all out, you get a simple quadratic equation. Lambda quarters minus 10 lambda plus 0.6875 equals 0. And now we just solve that quadratic equation to find our eigenvalues. The two solutions are lambda 1 is approximately 9.64 and lambda 2 is approximately 0.36. We found them. So step 3, eigendecomposition, is complete. After finding the corresponding eigenvectors for each of those eigenvalues, we have our two eigenpairs. Pair 1 has an eigenvalue or importance score of 9.64, and its direction is the vector 0.53, 0.85. Pair 2 has a much smaller eigenvalue, 0.36, and its direction is negative 0.85, 0.53. The hardest part is over. Let's finish the recipe. Step 4, sort the eigenpairs. This is easy. The y is to rank our new axes from most to least important. We just look at the eigenvalues. Since lambda 1, 9.64, is much bigger than lambda 2, 0.36, our ranking is simple. PC1 is the direction v1, PC2 is the direction v2. Done. Next, step 5, project the data to get scores. So why do we do this? We need to find the new coordinates for our original data points in this new PC coordinate system. The action is to multiply our centered data x by a matrix W, which is just our sorted eigenvectors stacked together. Let's build W and project our first centered point, which was negative 2, negative 3. You can see W is just our two eigenvectors, v1 and v2, as columns. We multiply the point, negative 2, negative 3, by this W matrix. The new PC1 coordinate is negative 2 times 0.53 plus negative 3 times 0.85, which is about negative 3.61. The new PC2 coordinate is negative 2 times negative 0.85 plus negative 3 times 0.53, which is about 0.11. So our new point is negative 3.61, 0.11. We just repeat that for every point. And now for step 6, the final payoff, explained variance. Why do we do this last step? To quantify exactly how much information we keep when we discard less important components. The action is to use this beautiful formula. The explained variance of a PC is just its eigenvalue divided by the sum of all the eigenvalues. Let's do the calculation. The total variance is just lambda 1 plus lambda 2, 9.64 plus 0.36, which is a nice clean 10.0. So the variance explained by PC1 is 9.64 divided by 10.0, which is 0.964. The variance explained by PC2 is 0.36 divided by 10.0, which is 0.036. And here is the final stunning result. PC1 captures 96.4% of the total variance. PC2 captures the remaining 3.6%. The recipe is complete. You've executed the recipe. You saw it work. But let's be honest. It might feel like magic. Why that specific recipe? Why the covariance matrix? Why its eigenvectors? This chapter is the proof. We are leaving the how and entering the why. So here's our detective story. We have two big questions to answer. First, why do we use the covariance matrix, sigma? What's so special about it? And second, why are its eigenvectors the ultimate answer to our problem? Our goal is a mathematical hunt. We need to find the unit vector u that maximizes the variance of our projected data. Our starting point is this simple expression. Maximize the variance of xu. Okay, let's start the hunt. We'll take this step by step. First, let's just give our projected data a name. Let's say z equals xu. Easy enough. Second, let's use the textbook definition of variance. For our centered data, the variance of z is just 1 over n minus 1 times the sum of the zi squared values. Third, in vector notation, this sum of squares is much cleaner. It's just 1 over n minus 1 times z transpose z. You can see how we're simplifying things already. Now, for the key move, step 4, we substitute z equals xu back into our equation. So, the variance of xu is 1 over n minus 1 times the quantity xu transpose times xu. Okay, stick with me here. For step 5, we apply a standard transpose rule. The transpose of AB is B transpose A transpose. So our expression becomes 1 over n minus 1 times U transpose X transpose times XU. And for step 6, we just regroup the terms. We'll put parentheses around the middle part. So we have U transpose times the quantity 1 over n minus 1 x transpose x times U. Stop. Look closely. That term in the middle, 1 over n minus 1 x transpose x, does that look familiar? It's the covariance matrix sigma. It's the exact formula we used in our recipe. And this leads to an inescapable conclusion. The variance of your data projected onto any direction U is given by this beautiful, compact formula. The variance of xu equals U transpose sigma U. It isn't a choice. It's not a convention. It's mathematically inevitable. So the hunt continues, but now we have a much clearer target. We've proven that our original problem, maximizing the variance of xu, is the exact same problem as maximizing U transpose sigma U. But that leads to our second question. Why is the answer to this problem the principal eigenvector?
I'll give you the answer up front because this is a cornerstone of linear algebra. It's a famous theorem. It says the unit vector u that maximizes the quantity U transpose sigma U is, and always will be, the principal eigenvector of the matrix sigma. And the maximum value it achieves is the corresponding largest eigenvalue, lambda 1. So let's prove it. The proof has two parts. First, we'll prove the variance in the direction of the principal eigenvector v1 is exactly lambda 1. And second, we'll prove that no other unit vector u can possibly do better. All right, proof part 1, the variance of an eigenvector. We start with our variance formula, U transpose sigma U, and we just plug in the principal eigenvector v1. So we have v1 transpose sigma v1. Now from the very definition of an eigenvector, we know that sigma times v1 equals lambda 1 times v1. So we can substitute that right in. Our expression becomes v1 transpose times lambda 1 v1. Next, we can just pull out the scalar eigenvalue lambda 1 to the front. So now we have lambda 1 times the quantity v1 transpose v1. And finally, since v1 is a unit vector, its dot product with itself, v1 transpose v1, is just 1. So we're left with lambda 1 times 1, which is simply lambda 1. Okay, so the variance is lambda 1. But is this the maximum? How do we know for sure? This brings us to proof part 2, and the key here is a concept called spectral decomposition. It sounds fancy, but the idea is simple. Any unit vector u can be written as a unique mix of the eigenvectors. So u equals c1v1 plus c2v2, and so on. And because u is a unit vector, the sum of these squared coefficients, c1 squared plus c2 squared, and so on, must equal 1. When we use this decomposition, our variance expression u transpose sigma u transforms into something really insightful. Lambda 1 times c1 squared plus lambda 2 times c2 squared, all the way to the end. And now, for the final move. The mic drop inequality. Here's the final proof. We know the eigenvalues are sorted from largest to smallest. Lambda 1 is greater than or equal to lambda 2, and so on. Now look at our variance expression again. Since all the other lambdas are smaller than or equal to lambda 1, we can replace them all with lambda 1 to create an inequality. The expression must be less than or equal to lambda 1 c1 squared plus lambda 1 c2 squared, and so on. Now we just factor out lambda 1. This gives us lambda 1 times the quantity c1 squared plus c2 squared plus all the others. And what do we know about that sum of squares in the parentheses? We know it equals 1. So our expression is less than or equal to lambda 1 times 1, which is just lambda 1. And there it is. For any unit vector u, the variance u transpose sigma u is always less than or equal to lambda 1. The variance in any direction can never exceed the largest eigenvalue. The only way to hit that maximum is if u is exactly v1. Let's summarize the unbreakable logic of PCA. Look at this table. We started with a concept, our goal. The math was to maximize the variance of xu. Then we simplified that variance, and the math showed it simplifies to u transpose sigma u. The conclusion? We have to use sigma. There's no other choice. Next, this gave us a new optimization problem. Maximize u transpose sigma u. This is a famous problem. The solution vector u that achieves this maximum is proven to be the eigenvector v1. And the maximum value itself? That's the value of v1 transpose sigma v1, which is proven to be the eigenvalue lambda 1. Eigendecomposition isn't a trick. It's not a clever hack. It is the fundamental solution to the hunt for maximum variance.
You've done it. You've mastered the how and the deep why. You understand the covariance matrix, the eigenvectors, the entire elegant proof. But now, we step out of the textbook and into the real world. And in the real world, there are some practical questions we have to answer. In this chapter, we're going to cover 3 critical practical tips for using PCA. First, standardization. When and why you need to scale your features. Second, choosing the right number of components to keep, using a tool called a scree plot. And finally, the most important part, interpreting your results using loadings and scores to tell a story with your data. Okay, first up, standardization. And here's why this is so important. There's a trap, a simple, devastating trap that can make your entire analysis completely meaningless if you get it wrong. PCA is blind to the units of your data. Let me show you what I mean. Imagine you have a dataset of athletes with 2 features, but they're on vastly different scales. Let's say we have height measured in centimeters, so you have values like 180, 192. And then you have weight measured in kilograms, values like 75, 81. Now, think about the variance of these 2 features. The variance of height with those big numbers is going to be in the hundreds, but the variance of weight with its smaller numbers will be in the tens. And what's the one thing we know about PCA? It is obsessed with variance. That's all it cares about. So PCA is going to look at these numbers and mistakenly conclude that height is overwhelmingly more important than weight. Not because it's a better predictor of anything, but simply because we measured it in centimeters. If we measured height in meters, like 1.8 meters, the exact opposite would happen. Suddenly, weight would seem more important. Your entire analysis would depend on the arbitrary units you chose. That's a disaster. So what's the solution? We have to put everyone on the same scale. Listen carefully. Before you ever run PCA on data where your features are on different scales, you must standardize. The action we take is called standardization, or calculating the z-score. The formula is simple. X scaled equals the original X minus its mean mu, all divided by its standard deviation, sigma. What does this do? It transforms every single feature column so that it has a mean of 0 and a standard deviation of 1. This gives every feature an equal footing. It removes the arbitrary influence of units and lets PCA find the true directions of maximum variance. So here is your rule of thumb. It's very simple. If your features have different units, kilograms, centimeters, dollars, whatever, you always standardize. No exceptions. If all your features have the same unit, for example, they're all pixels from an image, it's optional, but honestly, it's often still a good idea. It doesn't hurt. Okay, your data is now perfectly prepped. It's centered, it's standardized. You run the PCA algorithm, and this leads to the single most common question people ask. How many components do I actually keep? Because remember, the goal is to throw away the noise and keep the signal. The first method is a great visual heuristic. It's called the scree plot. Here's what one looks like. It's basically a line graph showing how much variance each principal component explains, from most to least. Now, when you look at this, you are looking for one thing, the elbow. See how the line starts steep, like a cliff, and then it flattens out into a gentle slope? That turning point is the elbow. The components before the elbow, that's your signal. Those are the important ones. The components after the elbow, that's the noise, the rubble at the bottom of the cliff. In this case, it looks like we should keep the first 3 components.
Okay, the visual method is great, but sometimes you need a more quantitative goal. For that, we use the cumulative explained variance plot. Here's what that looks like. Instead of plotting each component's variance by itself, we plot the running total. And how do you use it? It's simple. First, you set a target threshold. A really common one is 95%. Then, you just find the number of components required to cross that line. This gives you a clear, defensible statement for your project. You can say something like this. We reduced the dimensionality from 50 features down to just 12 principal components, while confidently retaining 95% of the total variance in the original data. See how powerful that is? Massive simplification, minimal information loss. All right, you've done the hard work. You've prepped the data. You've chosen your components. Now what? You have these abstract mathematical vectors. This is where most tutorials just stop. But this is where we turn abstract numbers into a concrete story. To do that, you need to understand 2 key outputs, loadings and scores. Loadings tell you what your new components mean, and scores tell you where your original data points land in this new, meaningful space. First, let's talk about loadings. The best way to think about them is naming your ACIST. Let's use a car dataset as an example. Say our features are horsepower, weight, MPG, and number of doors. After we run PCA, we look at the loadings for PC1. The loadings are basically the recipe for building that component. So for PC1, the recipe might look like this. V1 equals 0.6 times horsepower plus 0.5 times weight minus 0.4 times MPG plus 0.1 times doors. So how do we read this recipe? 3 steps. First, look at the magnitude. Horsepower, weight, and MPG have big numbers. They're important ingredients. Doors has a tiny number. It's not very important for PC1. Second, look at the sign. Horsepower and weight are both positive, so they vary together. As one goes up, the other goes up. But MPG is negative. It varies inversely. As horsepower and weight go up, MPG goes down. Which makes perfect sense, right? So, third step, give it a name. What is PC1 really measuring? It's measuring big and powerful versus small and efficient. You've just translated an abstract vector into a meaningful concept. Now for the final payoff. Part 2, the scores. The scores let us plot the story. This is the hero graphic of any PCA analysis, the scores plot. It's a scatter plot of all your data points, but instead of the old messy axes, the axes are now PC1 and PC2, our new super informative dimensions. Here's what one might look like for our car data. The x-axis is PC1, which we just named big powerful versus small efficient. The y-axis might be PC2, which could represent something like luxury versus basic. Now, how do you interpret this beautiful plot? First, look for clusters. See those groups of dots? Those are similar samples. PCA has automatically discovered these groupings in your data without you telling it anything. Next, look for outliers. Points that are far away from others are unique, and they warrant investigation. Maybe that's a rare electric sports car. Finally, look at the trends. The axes are now completely interpretable. Moving from left to right on this chart literally means moving from small, efficient cars to big, powerful ones. This is the ultimate goal. You take the abstract math, use the loadings to give your new axes meaning, and then use the scores to plot your data and reveal its hidden structure.
All right, let's take a deep breath and look back at what you have just mastered. We've covered a ton of ground, from the deep theory to the practical application. Let's boil it all down. So what was the core goal of all of this? The goal was to find the orthogonal directions of maximum variance in your dataset, to cut through the noise and find the signals that truly matter. And what was our primary tool for this quest? The covariance matrix. As you see in this formula, sigma equals 1 over n-1 times x transpose x. This simple-looking matrix is incredibly powerful. It encodes the complete variance structure of your data. Everything you need is locked inside. But a locked box needs a key. And our key, our engine, was eigendecomposition. As this diagram shows, it's a beautiful process. We take the covariance matrix, sigma, and we feed it into the eigendecomposition engine. And what comes out? 2 things. The eigenvectors v, which are the principal components, the new directions we were looking for, and the eigenvalues lambda, which tell us exactly how much variance is captured by each one. This is how we extract not just the directions, but also their importance. And we packaged this entire powerful idea into a simple, repeatable process, the 6-step recipe. You can see it here on the screen. Step 1, center the data. Step 2, compute sigma. Step 3, eigendecompose. Step 4, sort by the eigenvalues. Step 5, project the data. And finally, step 6, choose your components. That's the blueprint, from messy data to clean, interpretable insight, every single time. And we didn't just take it on faith, we went through the proof. We saw that our goal of maximizing the variance of the projected data, var of xu, reduces to the core problem of maximizing u transpose sigma u. And the solution to that optimization problem? It's the principal eigenvector. The math holds up, it's elegant, and it's correct. Then we brought it all back to the real world, the practice. You now have a checklist for success. You know to standardize features with different units. You know to use scree plots to find the elbow. You know how to use cumulative variance, like a 95% threshold, for a solid quantitative cutoff. You know how to interpret loadings to understand what each PC truly represents. And you know how to plot scores to visualize clusters, outliers, and hidden trends. This entire journey, it wasn't just about learning one algorithm. It was about building a foundation. You now have the key to understanding massive topics in machine learning, kernel PCA, the singular value decomposition, or SVD. A whole universe of advanced dimensionality reduction techniques is now within your reach. Because after everything we've been through, after all the math, the theory, and the practice, something fundamental has changed. You now see data differently.